Hello and welcome to our webinar, UAS Set to Revolutionize Public Safety. My name is Tony Grissom and I'm the Major Account Manager for Leica Geosystems Public Safety Group. I will be both your moderator for today's webinar as well as a presenter. My co-presenters today will be Rick Wyant of the Washington State Patrol and my colleague Brian Baker, who is our subject matter expert for the Leica Geosystems Aibot X6 Hexacopter, which is our featured but not our only technology that we will be briefing you on today. We're going to take a bit of a different approach to getting you spun up on our UAS technology in that we are going to share with you how the Leica UAS was deployed late last year at a large and complex crime scene that was part of a joint investigation by the Washington State Patrol and detectives from the Whatcom County Sheriff's Office. We feel that by starting you out with a problem statement of how to get that particular crime scene accurately and completely documented in 3D, we will walk you through our thinking behind our decisions that led to the deployment of specific Leica sensors. We will then describe to you the use of those sensors and the software and show you the exhibits which were created for the manslaughter trial. The third part of our program today will be a deep dive into the Leica UAS solution to include an overview of FAA regulations and what you need to do as a police agency to start deploying UAS. We have a broad cross-section of law enforcement, including many crash investigators present today in our audience. And I want to stress at the outset that even though this presentation will focus on a crime scene, that the information presented will absolutely be germane and relevant for crash reconstruction. Our two presenters today, besides myself, Rick Wyant is the Forensic Firearms Unit Supervisor for the Washington State Patrol Crime Lab in Seattle. He's been a forensic scientist since 1995, and he specializes in firearm and tool mark identification, crime scene analysis, less lethal devices, and trajectory reconstruction. He is an author of a book on less lethal devices. Rick has traveled the world educating police agencies, scientists, students, and attorneys. He's a distinguished member of the Association of Firearm and Tool Mark Examiners, and he's an associate member of the American Academy of Forensic Sciences. In his spare time, Rick is a level 1 reserve deputy for a major sheriff's office. Our other presenter today is Brian Baker. Brian is the UAS sales manager for Leica Geosystems. He's an instrument-rated pilot with almost 30 years of experience in the geospatial profession, focusing on management, software and application development, training, technical support for both land surveying and geographic information systems, and now UAS. During that time, he's become increasingly involved with developments in the UAS market, including FAA regulations. Before we begin, I'd like to give you a few tips. You should see on the upper right-hand side of your screen a widget bar. You can click on Help for an online technical fact if you need assistance. To make the slides on your screen larger, click the full screen button. If at any time you would like to ask a question, please enter it in the question box. This is a Q&A session, and we welcome your questions, and we will do our best to address as many as we can later in the presentation. But understand that due to the large number of people that we have, and it's hundreds, it's unlikely that we're going to be able to get to them all. If your question isn't answered during our live session, someone will reach out to you after the webinar. Before we get started with our first presenter, Rick Wyant from the Washington State Patrol, we're going to run a couple of quick poll questions by you and then share the results. So at this point, you have a poll up on your screen and the ability to answer yes or no. So the question is, does your agency currently deploy helicopter or fixed-wing aircraft? Please take a moment and select yes or no. And the results are about 40% say yes, about 60% say no. That's very interesting. And then we have one more poll question. We're jumping around a bit. Is your agency considering deploying UAS technology? Yes or no? So we try to stay away from using the term drone because it has a bad connotation to some people. Unmanned aerial systems, we emphasize the systems because of the technology that can be put into the payloads. So 83% of our respondents say yes, that's great. Okay, thanks for participating in the poll. I just want to review the agenda one more time before we get into and back up just one slide if you would please, Rick. As I said, I'm going to do a quick introduction of who our company is, Leica Geosystems. Section 1 is going to be the crime scene presentation by Rick. Then I'll be doing the technology deployment part of it. And then finally, Brian is going to be doing the deep dive into our UAS solution to include the FAA regulatory update. Then we'll get into the questions and answers. So the next slide, just briefly, I wanted to give you a snapshot and give you an understanding of who Leica Geosystems is. Our company is almost 200 years old, and it's been around in one form or another since 1819. We're one of the world's premier providers of geospatial measurement equipment. We're part of the Hexagon group, and today we're going to be focusing on several technologies. If we can go to the next slide here, we have a wide variety of technologies that can be deployed at any particular scene. One of the advantages are that they work seamlessly together, and we're going to be talking about several of these. But as we're looking at this particular slide here, at 12 o'clock obviously is the Aibot X6, our UAS system. Over to the right at 3 o'clock is our GS14 GPS system, which we used on this case. Down about 5 o'clock is the ScanStation. At 6 o'clock is the world's first multi-station. It's a combination of a total station and a 3D laser scanner. And then over about 7 or 8 o'clock is what's called our Pegasus 2 system. This is a mobile mapping system that can be mounted on any vehicle, and it takes the Leica ScanStation P20 series, mounts it onto the vehicle, and you can drive down the road at 50 miles an hour doing very high accuracy mapping. So at this point, I'm going to ask Rick Wyatt to take over and talk to us about his involvement in this case.
Good morning, everybody, or afternoon if you're not on the West Coast. I'm going to briefly go through this case that we had submitted to us, a long-distance shooting involving the death of a young woman. We don't normally get long-distance shootings, as you would imagine, at least any that need or require any kind of reconstruction to really understand what happened. And it was a really nice joint effort between the Whatcom County Sheriff's Office, State Patrol Crime Lab, Leica Geosystems, and Luke Haig, who's one of our godfathers of firearm toolmark examination, helped contribute greatly to the data that we were able to get on the bullet behavior of this particular firearm. So that's a picture of him down on the bottom, and you'll see more of them as we go along here. This is our victim. It was a Father's Day barbecue, and she was in her backyard at her grandma's house, and a stray bullet entered her and went right through her heart, and she was pretty much dead on the scene. There was some suspects that were located on a riverbank shooting firearms some distance away, and they were apprehended. Their firearms were seized, and we started the investigation from there on trying to determine what happened. That's her entrance wound. It's an atypical entrance wound. Tells us a couple of things, but it entered about her upper right chest, through her heart, and stayed in her body, which of course is a clue to us firearms nerds when a rifle bullet doesn't exit and stays intact, that we have something going on other than a typical rifle shot. And that's the bullet, nearly intact. And there's a couple things that tells us, and either it's a long distance shot or there's something wrong with the ammunition, etc. So we're starting to put it together on what occurred. Well, there's some previous research that Luke Haig, the previous gentleman I talked about, did on bullets impacting materials, and they will stay intact at certain velocities. So we had a pretty good idea what our velocity was, strictly based on the fact that the bullet didn't deform. Here's our crime scene. I'm just taken off of Google Maps, and here's our victim in the backyard, and then the shooter about 800 yards away and about 18 feet up in elevation. So kind of a miracle shot in terms of what we see normally in the crime lab. But we had a couple of questions we needed to answer, and I'm going to go through them now. Here's the firearm. This is a Sega. It's a AK-47 variant. There's the ammunition, Ukrainian steel-jacketed ammunition. And so based on that, we have a pretty good idea how the bullet's going to behave. There's the chart, ballistics chart that you'll see if you research any kind of modern firearm ammunition. And at about 800 yards, it's going about 900 feet per second, 850, 900 feet per second, an energy of 196. And if you look on top, it's dropping significantly from muzzle at 1,500 foot-pounds of energy. And what's also interesting to note, at 800 yards, it's dropping 511 inches, which is a pretty significant drop in bullet as it travels downrange. So there's our view from our shooter, and our victim is through the trees. I don't know if this pointer works, but through the trees about right in here. So I did a little field research. I got U.S. Customs to give me a flight so I could see it from the air. And as you can see, 800 yards is a long way. And there are different types of topography. We have a riverbank, we have flat field, the trees, and then right at the end of the video will be the backyard. So at this point, all we really had was an aerial shot and some total station data taken, and we really needed to map that scene a little more accurately to answer our questions. So here's our view from the air. There's our victim. There's our shooter. There's our distance. And again, 18 feet elevation. So there's three possible ways that that bullet could have struck our victim. One is a falling bullet. Shot straight in the air. It happened to fall right where the victim was standing. Second shot's a direct shot, just high enough to clear the riverbank and managed to go through the trees and strike her. And then the third shot, which was the problematic one for us, did a ricochet off the water. And of course we're looking for malicious use of the firearm, we're looking for intent to cause bodily harm, lack of safety, etc. And a ricochet off the water would point toward more just a freak accident versus negligence. So this is what we're trying to show for the prosecutor. So a direct shot, about 511 inches, about 42 feet of drop, so it's dropping almost 50 feet at 800 yards. And the victim's about 18 feet higher than the shooter. And so we're looking at about a 20-yard drop. And so what's the angle of shot to the victim? It's only about 1 to 3 degrees of of inclination of that barrel to reach that distance. So that's the one question we wanted to answer is, was a direct shot possible? Now the previous research on bullet ricochets, you might find surprising that the bullet will stay intact almost all of the time when it hits water at low angles. Now our 1 to 3 degree would fall into that category. So the bullet does not fragment, in fact will bounce off the water almost entirely intact. So we cannot rule out a ricochet shot at this point, strictly based on how the bullet looks. So we did field research number 2. Went down to Arizona where Luke Haig lives, and of course there's lots of vast expanse to shoot any number of experiments that you want and not have to worry about offending anybody. So we did some 800-yard testing, put some ballistic gel out at 800 yards and actually tried to hit it, because if we could collect a bullet striking ballistic gel at 800 yards, we can compare the depth of penetration versus our victim and again try to put that piece of the puzzle together. So just to give you an idea of how far that is from a shooter's perspective, those vehicles are 200 yards away and we're shooting almost to the crest of the hill there to achieve an 800-yard range. In fact, we had 4 shooters, and depending on who you ask, they are experts, and we had a really hard time hitting a torso-sized target at that range with that particular firearm and open sights. So enter the Doppler radar. Now the Doppler radar is basically the same technology that you see for weather analysis, but this particular type of system will track a bullet and do incremental velocities all the way out to, well, probably 200 or 300 yards. And we can take that data and extrapolate the behavior of that bullet as it travels downrange. The great thing about the Doppler radar is if that bullet is unstable or destabilized, it tells us very successfully that that bullet is not traveling the way it should, and we'll give it that incremental velocity as it travels downrange. So typically this particular firearm ammunition will give us about 2,300 feet per second and a ballistic coefficient of 0.288. I won't bore you with the science behind ballistic coefficient, but basically the higher the number, the more stable the bullet is. So this is a direct shot, and that wave on the top chart shows that the bullet is stable, and the bottom chart is the velocity over time. So at 100 yards, it's dropping about 200 feet per second, and it's nice and stable. You got a nice straight line. So Luke found us a water test facility. It's an old pond out in the middle of southeastern Arizona, and we were able to conduct ricochet testing on this particular body of water and track it with Doppler radar. So there's the setup. There's a still of the bullet ricocheting off the water. And how we calculated the angle of departure is we set up 2 witness panels at a known distance from each other and then calculate the height off the water of its impact. And between those 2 points we can determine the angle of departure, which is important to us if we want to know how far downrange that bullet is going. Some of them are leaving at about 9 degrees. And now we're seeing a little different chart on our Doppler radar. It's a nice straight line, and then when it impacts the water, you can see the bullet very destabilized and the velocity dropping very rapidly. It's also interesting to note that the bullets will keyhole, meaning they'll turn on its side. And the bullets are so destabilized that they're hitting our witness panel about 10 feet from the water impact site sideways. So here's some of our raw data taken from the Doppler radar. Now, these are the straight shots with no ricochet, and if you look at the bottom red square, you can see at 800 feet traveling about 919 feet per second, which is pretty close to that ballistic chart that I showed at the beginning of the presentation. So what they published versus what we were recording was pretty accurate. Our drop in inches was about 500 inches versus the 511 that they calculated. So everything is on par with what we expected to see. Enter the ricochet bullet at 100 yards, and we're only able to measure it out to 700 yards, but it's only going 233 feet per second at that range. So dropping significantly, and it's losing that energy as it's flying through the air because the bullet is tumbling and it's destabilized. And we did about 30 shots, and almost all of them have the same data, roughly. So summarizing, our direct shot would be about 1 degree of angle departure, 919 feet per second or so, and then less than 200 feet per second for our bullet at 800 yards that ricocheted off the water. So all this said and done, we're starting to put a picture together of how that bullet behaved and how it was fired and how this young lady lost her life. And what we hadn't talked about is the falling bullet. These are trajectory envelopes calculated from Yuma Proving Ground. We used to go out there and use their Doppler radar years ago, and this is some old data on this particular type of ammunition. And so we fire a bullet straight in the air, and that's the range that it will reach before at different angles. Sorry. So it achieve a maximum distance of about 28 or 32 degrees angle departure. That'll get you about 3,500 yards downrange. And of course our victim is about here. So need about 80 degrees or so straight in the air for that bullet to fall and strike her. Now we have a couple problems with that, of course, being the angle of entry into her, assuming she's standing upright. That wouldn't fit our model here. But in addition, a falling bullet, because when you fire a bullet straight in the air, the velocity is terminal velocity as it falls back to Earth, and we're looking at about 200 feet per second if it falls base first, and if it's tumbling, about 158 feet per second. So our velocities are about the same as a falling bullet as a ricochet bullet at that distance, which is interesting to note. So here's a summary of our chart of all the testing that we did. And so, again, trying to answer those three potential possibilities of that bullet travel: a direct shot, a ricochet shot, or a falling shot. And our departure angle, about 1 to 2 degrees, is going to give us about 900 feet per second. And our tissue penetration is about 12 inches, which is about the tissue penetration, or the penetration of the bullet into our victim. So everything is pointing toward a direct shot versus a ricochet or a falling bullet. What's also interesting to note is 200 to 250 feet per second is what we measured on the falling and ricochet bullet. And if you calculate the muzzle energy of the weight of that bullet and the velocity, it's similar to a pepper ball, which is a less lethal weapon, obviously not designed to penetrate or cause injury. So we're looking at pepper ball type of muzzle energies or impact energies with the ricochet or falling bullet. So we're about 0 to 2 inches of estimated penetration, which isn't consistent with what we saw in our victim. So our last question, this is where I brought in Tony, was the shot possible with the scene topography? Now we had some total station data and we had some Google Map or Google Earth data, but we wanted to map that scene a little more accurately because it was such a vast scene and such an incredible and possible shot. And so I contacted Tony because I know him, I'm very familiar with him with our 3D scanning that we brought to Washington. And my initial thought was to walk two systems together. Start one at the victim and start another one at the suspect or where the shooter was, and then walk both of them together and commingle the data. And so that would map the scene for us accurately. Well, after talking to him, he mentioned that he might have a new technology that he can employ for this scene that would be quicker and more efficient for us as we're out there measuring it. And so I'll go ahead and pass it over to Tony so he can talk about what he did on his end. If I can find him on this really long list.
Just hit the change presenter button upper right. There we go.
Yeah, but it lists everyone who's here, so I have to find your name. Hang on a second.
Okay, I'm assuming you guys can see my screen. So this particular crime scene presented some challenges, and it really wasn't until I could get out on the ground and walk it that I decided how we needed to go about approaching the topographic mapping of it. So we had the shooter on the riverbank, had the victim in the back of the house about 800 yards away, and I walked down to the river and I took a panoramic photograph with my smartphone just to sort of give you the on-the-ground view of it. The shooters were over across the river on the left, and then this is about 240 degrees worth of panorama. The tree line in the upper right is where the house is. And it became clear to me that while the UAS would be just absolutely ideal for capturing the vast expanse between where the shooter was versus where the victim, we really wanted to also do some detailed terrestrial laser scanning in the areas in yellow, which is the back of the house and right where the shooters were. So I have a sort of a basket of products to choose from, and we ended up deploying several of them, and we're going to get into those right now. So the primary tool was the drone, if you will, the unmanned aerial system. And for this, we used the Leica Geosystems Aibot X6. It's a hexacopter. I'm going to probably mention a few of its features and attributes, but I'm going to be saving most of it for Brian's portion of the presentation after I present. We also used one of the Washington State Patrol's Leica ScanStations, in this case the PS20. And I'm just going to stop for a minute and take a minute and go through some of the primary features of this particular technology. This is a terrestrial 3D laser scanner with an accuracy of 3 millimeters, 50 meters away from it. That's 1/8 of an inch. And that's 3D positional accuracy. It's an all-weather system that can be used in the sun, in the rain, in the snow, and in the wind. It has an operating temperature range of -4 degrees Fahrenheit in the low end to 122 Fahrenheit. It's long range. It can capture up to 1 million measurements per second. We offer a complete solution from the Leica Public Safety Group, including our Cyclone software, which is an industry standard for point cloud data processing. For those of you who work for accredited crime laboratories who are part of the ISO 17025 program for accreditation, we have mistraceable compliance. The training that's provided through our public safety group is approved by the IAI. For those of you who are seeking to maintain your certified crime scene analyst certification, and we've also received a federal Daubert ruling on the Leica ScanStation and our Cyclone software, which took a lot of work to do, but we're quite proud of it. We also have 2 other ScanStation models available. I'm just going to focus on this one today, but we'd love to talk to you about it if you're interested. So the ScanStation technology has been around some time. This is an Associated Press photograph from about 1.5 years ago out in the street in front of the Washington Navy Yard, when actually 2 of our customers from the Metropolitan Police Department in Washington, D.C., attached to the Consolidated Forensic Laboratory, along with the Metropolitan Police, they deployed 5 ScanStations in support of the FBI's investigation of this active shooter incident. This was a multi-agency response. These agencies had trained together, and they had 5 of them out in the street within an hour after the first shots were fired. They did an outstanding job. They were able to get 5 floors of this building 197 scanned. That's 5 floors, about 1 million square feet of office building in about 6 or 6.5 hours. And I think they also got the shooter's car in the garage during that same period of time. They processed all that data using Leica's Cyclone software, which we're going to come back to, and they published it using Leica TrueView. So back to our scene. So one of the first things that we did in preparation for flying this scene with the UAS is we used the mission planning software that comes with the system called Leica iPro Flight software. And at the hotel in the morning before we drove out to the scene, is we preloaded up in a cache, if you will, some background imagery from Google Earth, so that when we were out there working on the back of the vehicle trying to figure out our flight lines, we had that imagery already stored. It was determined that we really needed to have 2 flight lines in order to do the data capture that we wanted to. One of the things I wanted to mention is that this software does support the importation of waypoints. So if your agency or your county has a geographic information system and you know where the public right-of-way is versus the private property, or you know where the airspace is that you might be concerned about because there's an airport nearby, the software inside the UAS has the ability to have an envelope that you can restrict its access to. So for those who might have privacy concerns, or maybe the search warrant doesn't extend into an area that they're might possibly fly near, you have the ability to control the flight path of the system. So the thing about capturing data in 3 dimensions is that essentially it's a photogrammetric technique. And the photogrammetry has been around for years. You take photographs with a camera, and you're either in an airplane or in our case with a UAS. And in order to be able to stitch all of the hundreds of photographs taken together, you need some sort of a photo control point down on the ground to provide that stitching capability within the software. If you've ever driven around out on the highway and seen a surveyor set up on a big white painted X, it's the same thing, only the photograph's being taken by an airplane. So we decided that we needed some photo control points. So we went down to our local Home Depot and we purchased some 4-inch square white ceramic bathroom tiles, which showed up just beautifully in the photos taken by the UAS, the Aibot X6. But in order to tie those all together geospatially correct in 3D, I decided that we needed to deploy the Leica GS14, which is our GPS unit that captures positions using a technique called real-time kinematic. Now, for those of you not familiar with real-time kinematic GPS surveying, there's a base station involved somewhere, and a correction is broadcast over to the person running the GPS rover, is what we call it. That correction is required in order to get those centimeter level positions on whatever it is that you're locating, in this case the photo control points. However, I had another option. Because I didn't want to take the time to set up my own reference station, I took advantage of some infrastructure that Leica Geosystems has established all over the country in a lot of different states, a lot of different geographic areas. It's called the SmartNet. This is a series of Leica-owned and operated, for the most part, reference stations that are constantly monitoring satellites, and then the information is captured by a computer system, and then these RTK corrections, real-time kinematic corrections, are broadcast to an infinite number of rovers to a fairly inexpensive system, the GS14, and this is done over regular cellular technology. So the satellite signals come down from space, and it's a constellation that includes both the American GPS satellites as well as the European satellites, and the correction is broadcast to the rovers, and bang, we get a centimeter level position. So the SmartNet that I'm referring to is quite dense in the major geographic areas in Washington State, and it just so happens that there was a SmartNet reference station just a few miles south of the crime scene, and that was the primary one that was providing us the corrections in the field. So that's two different Leica technologies brought to bear before we ever got the drone up in the air. So the other technology was the ScanStation. And I know this photo isn't great, but you can see the ScanStation PS20 in the foreground on the right. And the thing I'll point out to you is it's shaded because it's almost under a tree. Now, the victim fell in this little garden area where they planted some roses that you see off to the left there in the middle. The thing I wanted to point out is that there was no way I could get a GPS position underneath this tree because, you know, it was too obstructed. But I was able to get a GPS position farther up into the backyard where you see the red circle, and I've got a single solitary laser scanning target plumbed up on a point that I set in the ground right there. So using one of Rick's photographs showing the scene, I decided that in order to be able to tie together all of the data captured by the UAS with the laser scanning data that I was capturing at the ground level under trees and elsewhere, I needed to operate the Leica ScanStation in a mode called traverse mode. Now those reconstructionists on the phone who are accustomed to a total station are familiar with this. You set a point in the ground, you pound a nail in the ground, for example, you plumb up your instrument, in this case the Leica ScanStation, over the position, you measure the height of the instrument, you backsight, and you start making measurements. So schematically speaking, this is what I had, my situation in the backyard. I had two stations that were obstructed by trees, one critical one up where the victim was, and another one down by the roadway. But I had three positions that I was able to use my GS14 rover to capture centimeter level positions on. And that was key to how we captured all this data and stitched it together. So one of the benefits about traversing with the ScanStation is that you only need one target, and the scans that you capture are automatically registered on board the scanner, or they're aligned. That means you don't have to do any data processing to pull all the data from many, many stations together. It also facilitates easy integration with those of you already using total stations, because the same monuments or nails in the ground that you use for the laser scanning can easily be used for the total station work as well. And then the data is all on the same coordinate system. As far as the distance that I've personally measured between a target, I've gone 85 meters, which is about 270 feet. This is a very long-range instrument. It's a very powerful part of one of the workflow options that you have. So once we got out there, we decided we needed to set nails so that we could operate the ScanStation and traverse operation. So there's one of the WSP guys helping me out, setting a 60 penny nail. I also set stations down by the river. Of course, it was wide open down there. I didn't have any visibility problems. But the operator, a guy named Trevor from the WSP, he had never operated his ScanStation in traverse mode. It took me about 20 minutes to teach him how to do it, and we left him alone, and he nailed it on both sides, both in the backyard and down by the river. He located about 8 stations, and this was a big part of the data collected. So we staged all of our equipment in the field. We had, lots of police vehicles and private vehicles right where we were ready to launch, and then we flew the missions. And I'm going to let Brian talk more about the details of the UAS. But in the picture on the left, you can see it. We were below 400 feet. We were in line of sight, and we ended up standing in the middle of this scene and flew about 400 or 500 feet in one direction, and then 400 or 500 feet in the other direction, and capturing photographs. One of the things that was absolutely key to capturing this successfully is the Leica Aibot X6 has the ability to ascend vertically, which with a fixed wing UAS, which requires essentially a runway and a lot of space to take off, you could have never really done what we did. But because we have the ability to launch straight up in the air vertically, it enabled us, the pilot I should say, was able to get this thing up over the trees in the backyard. And it's one of the big benefits from a safety standpoint as well, the ability to have control of the A6 directly over the site. So we took photos, we also laser scanned, and I measured a bunch of points using the GPS. So the data that we captured consisted of hundreds of photographs from the Leica Aibot X6. We got real-world coordinates courtesy of the SmartNet infrastructure using my Leica GS14 rover. And then, of course, we got tens, if not hundreds of millions of measurements from the Leica ScanStation. 3 different sensors were deployed. So this is sort of a snapshot of the data processing that took place. So the photographs from the Aibot X6 were downloaded into a piece of software that comes with the system called Agisoft PhotoScan. And when combined with the GPS coordinates that came out of the rover, a bundle adjustment was done, and a 3D model was developed, and we were actually able to show that to the district attorney's office and the detectives from the sheriff's office just after lunch. We got out there about 9 o'clock in the morning. We were pretty much done by 11 or 11:30. These flights only took like 7 minutes each. And we went and got some sandwiches and went back to the Emergency Operations Center, and we were looking at real 3D data of the scene within an hour or 2 afterwards. There was still some additional post-processing that was done after the fact, but we had pretty much real time. And so the data from the Agisoft PhotoScan software was exported as what's called LAS format. Now that's a LAS format's an international photogrammetry standard, and it came right into the Leica Cyclone software, which is the same software that's used by our public safety customers for doing things like shooting reconstruction or witness viewpoints or creating a lot of different products and deliverables that are sort of outside the scope of this particular webinar. But we obviously then took the ScanStation data and brought that into Cyclone, and then we generated some court exhibits. I'm going to finish my part of the presentation by showing you these exhibits before I turn it over to Brian. So I'm going to close up PowerPoint, and we're going to start by taking a look at what's called a fly-through. Now, this is animation, and because of the bandwidth, it's going to look a little bit jerky to you, but I assure you on my screen I'm seeing a smooth flyover of a large 3D data set that is a combination of terrestrial LiDAR from the Leica ScanStation and the UAS system, the X6. Now, we're coming over the ditch, we're heading down the road. We cut out most of the cars and the privately owned vehicles, and we're moving now over to the backyard where you can start to see the 3D model. What is this? This is a point cloud. This is hundreds of millions of measurements that were generated through a combination of photogrammetry and terrestrial 3D laser scanning. And I'm going to freeze it right here so that you can see that there's a leader line that shows you right about where the victim was hit by the bullet. And what we did in order to sort of emphasize this is that we did a 3D model. We created a 3D model of the shed and the fence in the backyard just to provide some perspective. So this is fly-through number 1, which gives you an idea of the scene, but the second one is more along the alignment of the bullet path. Not exactly the bullet path, it's just on this alignment that goes straight from where the shooter was to the backyard. So there's, in the foreground, you just saw where they were shooting through the trees, through the farmland. Here's the ravine. Here's where we were parked, where we launched from. I should say we did 2 flights from that middle part of the field, but then we did one more UAS flight from the backyard, and that's where the vertical ascent capability of the UAS really made a big difference, because we launched it out of an area over here to the right about the size of a half court of a basketball court. Very small area. So that was the first 2 exhibits. They're called fly-throughs of the point cloud. The second type of exhibit that was created is what's called a Leica TrueView. Now, Leica TrueView is a free viewing software that enables you to create something that's very user-friendly and easy to use. You can use it in court. You can hand it out to other experts. But it runs inside my browser, in this case Internet Explorer. And if I double-click on this triangle here down by the riverbank, it essentially takes advantage of the panoramic photograph capability of the ScanStation, because the ScanStation takes panoramic photos as well as captures these millions and millions of accurate measurements. And now I'm looking back to the backyard, and the shooters were down over here right towards the bottom of this trail. There's a little, I'm zooming in right now, there's a little trail that you can see that they walked down, and then they were standing somewhere in this area here when the shooting, the target practice took place. One of the other things that you can do in TrueView is you can easily make a measurement between anything you want. So there's a stick here on the ground. If I want to know about how far that stick is, the distance is, I can extract any dimension that I want. So TrueView allows you to attach photographs, reports, any kind of media can be attached to TrueView and launched, and it's free, and it allows you to easily share information with other professionals and to be able to put that jury into the crime scene. So with that, I'm going to change presenters now, and I'm going to ask Brian to do the overview, the technical overview on our UAS system. So Brian, if you will, please.
Thank you, Tony. All right, those are great presentations from Rick and Tony, and so I've got a little bit of time here to follow up on the technical side, and I've been trying to answer some of the questions that have been coming through on the question panel, and I'm not sure that we'll get to all of them, but I'm trying to get to some of them. So my focus of my presentation is on the technical side of the UAS, and we're going to talk about what is a UAS, the capabilities of rotary wing UAS, forensic applications as it relates to UAS, and then what several questions have come in on regarding the regulatory status from the FAA, and possibly a little bit, if we have time, on how UAS will change forensic applications in the future. And then the last part will be some questions and answers. So I anticipate that we'll probably be going 10 to 15 minutes after the hour. So first off, what is a UAS? And most of you have a pretty good idea. And it's not technically, it's not an unmanned aircraft system. It's a remotely piloted aircraft. There's a pilot, it's just not on board the aircraft. And that's a pretty important distinction in the mind of the FAA. But for most of it, it's not really the same thing. The other thing that's important is that the pilot's within visual line of sight of the aircraft. The FAA has not approved any air operations that are beyond visual line of sight. So the dream of having some sort of accident out on the road and going out from the police station, being able to task a drone to launch and go fly to that site and fly around it, take photographs, and then come back to the police station, that's quite a ways off. Not to mention getting your books via Amazon's drones, a long ways off. The unmanned aircraft system also is designed to carry some sort of payload. In our case, it's a sensor, not a book. And we use it for an aerial perspective for a crime scene or an accident scene, or also to remove a person from harm's way. So there are two different scenarios that this aircraft may be used in public safety. Of course, you've all heard about many different applications in many different industries for UAS. We're focused on forensics and law enforcement today. It's also known as a drone, an unmanned aerial vehicle, UAV, unmanned aircraft, and remotely piloted aircraft. Those are all acronyms for an unmanned aircraft system. And when we talk about system, we're talking about not just the aircraft, we're talking about the control unit, we're talking about the sensor, we're talking about the processing software. So we really are talking about the entire system. And that's what the FAA looks at as well. They don't just look at how good the aircraft is, but they look at the robustness of the control unit as well as pilot qualifications and that sort of thing. So there are a couple of different categories of UAS. Rotary wing, including helicopter and multicopter, which is what we're dealing with the Aibot X6. Vertical takeoff and landing capability, electric motors, fully autonomous or manually controlled flight, both have their applications. For city mapping, inspections, environmental mapping, reconnaissance, rapid mapping for smaller areas, and multi-sensor missions. A fixed-wing UAS, the other common category, and it's usually launched by hand or by catapult. It's generally sensor-specific because the aircraft is very, very sensitive to weight and balance. And so the aircraft is usually developed for a specific sensor, in some cases even for a particular model of camera. And a lot of times the payload package is not interchangeable. In addition, you usually need a much larger area for launch and recovery of a UAS, for a fixed-wing UAS. And you usually are only pre-planning those missions. It's fully autonomous because for mapping applications, you cannot manually fly a fixed-wing unmanned aircraft accurately enough to make sure that you get the mapping coverage that you need. So it's all automated and very little control of the aircraft aside from evasive maneuvering capabilities. If there's a safety issue, something like that, you need to bring the aircraft back immediately or end its flight immediately or take some sort of evasive maneuver to another area. And they're good for small mapping in agriculture, mining, reconnaissance, and some emergency response. So when we start comparing the two categories, rotary wing versus fixed wing, we see where the differences are in this matrix. For a rotary wing, you have both autonomous and manual flight control. The sensor is variable. The takeoff capability is vertical takeoff and landing. This is a big difference with a fixed-wing aircraft. You usually require a much larger landing zone. And in the case of our crime scene, we have plenty of room for takeoff and landing, but that's not going to be the case in an accident site at an intersection in a metropolitan area. The flight area for a rotor wing is usually on the smaller side of area, although you did see that we mapped quite a large area. We took a couple flights to do it. A fixed-wing aircraft probably would have done it in one flight. But all the other capabilities that we have with rotor wing gives us a lot more flexibility. Our payload on the rotor wing is small to medium, usually only very small in the fixed wing. Real-time video, yes. Hover capability, yes. And indoor use capability with rotor wing is possible. So here's a video of launching the X6. And you'll see that the time of deployment here is usually less than 1 minute. There are some safety checks and other things that we normally go through before deployment. We have a checklist that the pilot and command goes through. But essentially, the launch sequence is pretty straightforward and pretty easily accomplished. And then a recovery is along the same lines. The aircraft comes in, and in this case, this pilot's got a lot of experience, and he just plucks it out of the air, which normally you wouldn't do, but he does. So this is the Aibot X6, and what it looks like, it's a hexacopter. So when you start talking about multi-rotor aircraft, you have quadcopters, hexacopters, octocopters, and I've even seen a pentacopter. And there's a couple of reasons that we chose a hexacopter design. I'll go into those in a minute. The way that this flies is that it uses differential thrust and torque management of the multiple rotors for lift and directional control. So if we want to move forward with our aircraft, then the aircraft provides more thrust to the back rotor and less thrust to the front rotor, thus pitching the aircraft forward and moving it in a forward direction. And moving it backward is the reverse, and then moving it from side to side is where you would have it roll by increasing the thrust on the right side to roll to the left, and increasing the thrust on the left side to roll to the right. And then if you want to yaw or spin the copter around, it also changes the speed of the clockwise rotors and increases the clockwise rotation speed and decreases the counterclockwise rotation speed, and that causes a gyro spin of the helicopter to get it pointed in a different direction. It's highly maneuverable, and I keep touching on the vertical takeoff and landing capability. It has a fully automatic operation mode, meaning you can have the aircraft take itself off, fly a flight plan, and land itself, all with only 3 buttons. And the biggest thing is that it's designed with safety as the #1 priority. One thing that you're going to notice right away with our aircraft is that all of our rotors are shrouded. So they're enclosed with a carbon fiber airframe. This allows you to get close to objects for inspection. It also allows you to fly underneath objects like bridges. And if a gust of wind or an inadvertent command were to cause the aircraft to bump into a structure, it's not going to damage the aircraft or the structure. On an aircraft with unshrouded rotors, you're going to bust a propeller, possibly damage the structure, and the aircraft is going to come down if it's got damaged rotors. Our rotors are shrouded, and the other reason we went with a hexacopter design is that we can still fly on 5 motors. You can't do that on a quadcopter. So safety, again, being the #1 priority here. Carbon fiber construction. So the whole airframe is made out of carbon fiber. Shielded propellers, automatic takeoff and landing capability, and then it also has complete manual operation. You see a couple of joysticks here, not unlike most remote-controlled aircraft. And then we've designed it with a future enhancement in mind so that we can put on different sensors, possibly different types of payloads, that sort of consideration for future development. So talking about safety, I already mentioned the enclosed rotors. I also mentioned the automatic takeoff and landing capability. Another one that capability that this aircraft has is GPS hold. Basically, you can get the aircraft where you want it to be and let go of the sticks, and it's going to stay there, both horizontally and vertically. If there's some wind, it will adjust its thrust to compensate for the wind to keep it within that plus or minus about 1 meter position. A geofence, also known as a cage, is the ability to limit the flight of the aircraft, and Tony mentioned this a little bit in his presentation, but we can prevent the aircraft from flying outside of a particular area of interest that we're concerned about. Again, if it's a right-of-way issue, privacy, search warrant limits, things like that, we can conform our aircraft to fly only within that area. A fixed-wing aircraft, to actually capture the entire area, has to overfly the entire area, meaning that it has to fly beyond the extent of the scene to capture the entire scene. And depending on the speed of the fixed-wing aircraft, that might take some additional room for it to overfly and then turn around and come back. Carefree flight mode. It's a little difficult to explain if you're not familiar with how a rotor wing aircraft flies, but it increases the safety because you don't have to worry about the aircraft orientation to be able to control it. We have an automatic return to home mode, which is a fairly common feature. And we have a point of interest mode. So the aircraft can, you can define by hovering over an object a point of interest, and then once you tell it that that's the point of interest, the aircraft will back away from it, point the camera to it, and loiter in 360-degree circles around that point of interest with the camera trained on that object. It's an easy aircraft to fly. It's very safe to fly, and even if you are not an expert pilot, you can be trained up in operating this safely very quickly. Some specs on it. One of the biggest specs that we have is the payload capacity. So we can actually carry several sensors as long as they don't exceed 5 pounds. The more weight that you get on the aircraft, the lower the flight time. Also, the more wind that you're dealing with, the lower the flight time, just because it takes more power to compensate for those two increasingly adverse conditions. It will fly up to 38 miles per hour, so it can fly fairly quickly. And a flight duration of, if you had it fully loaded, it would be more like 15 to 25 minutes. 25 minutes is going to be on the high end with a very small camera. The sensor platform, this is another unique feature that you don't find on a lot of aircraft. It's a gyro-stabilized gimbal mount, meaning it compensates for the pitch and the roll of the aircraft to keep your camera pointed in the same position that you wanted it pointed into. So from a mapping standpoint, this is really important because as the aircraft pitches forward, the camera would skew backwards if it wasn't compensated for by our gyro-stabilized mount. And as the aircraft rolled to the left or rolled to the right, our gimbal compensates for that roll with the gimbal. So we get consistent image overlaps, fewer flight lines are required. We have a better vertical sensor orientation, and also this can be real-time controlled from the ground station. So you can you can tilt the gimbal from the ground station to either look straight down or straight out or basically wherever you want it to look. And if you have a video camera, you can see that video feed in real time. So then we start talking about the different sensors. Digital cameras are an option, anything from a fairly generic Nikon Coolpix camera all the way up to a very high-end SLR camera, whether it's a Canon or Nikon or Sony. We integrate different types of off-the-shelf sensors. So you don't have to worry about your aircraft becoming obsolete just because the sensor is obsolete. So yesterday's 16 megapixel cameras now today's 24 megapixel camera, which is very soon to be tomorrow's 36 megapixel camera. It'd really be a shame to have to get rid of your entire aircraft just because the sensor changed on it. So that's one of the future-proof capabilities that we've built in. We have other sensors, thermal imaging, and I'm going to go through these pretty quickly because I need to get to the FAA stuff. We're getting short on time. Scanning capability is coming sometime this year. First-person viewing is an option, and we have several options for that. And for public safety, forensic mapping and intelligence are the main applications for this type of platform. I'm sure you can probably put in some others too. But if it's launching missiles or firing guns, we don't really get into that. Okay, so now the million-dollar question that most people are asking is, what about the regulatory status of unmanned aircraft system? And the regulation is governed by the FAA. So if I have any pilots that are on today's presentation, they'll know that the FAA's unofficial motto is, we're not happy until you're not happy. And quite honestly, nobody is happy with the regulatory status of unmanned aircraft systems, including the FAA. But there is some progress. And the issues are our national airspace system. We have the most complex national airspace system in the world. And it's because we have such a large general aviation market. You don't have the general aviation market in other countries that we have in this country. By general aviation, I mean private airplanes, small airplanes, helicopters, just all kinds of general aviation activity. And because of a mid-air collision in 1956, the Congress mandated the FAA and the National Airspace System. And the mission statement is right here. And the mission of the FAA and the National Airspace is to protect persons and property on the ground, number one, and then to establish a safe and efficient airspace for environment for civil, blah, blah, blah. So the first mandated is to protect people on the ground. When you start thinking about UAS in those terms, some of the delays and regulations start making a little bit more sense. We have 5 different classes of airspace in the U.S., and as a pilot, you need to be aware of them and how to deal with them in all scenarios. Class A airspace is above 18,000 feet. Doesn't get involved in UAS operations or most any type of manned aircraft mapping applications. We're dealing with airspace down here in a couple of 100-foot area. But we still have areas around airports that are very congested and need to be handled in a very specific manner. This is what a pilot sees when he looks at a VFR sectional chart. This happens to be Denver International Airport in the center, and then there's concentric rings identifying the different elevations of airspace around the airport. And if you go back to the previous slide, you can see that this is the airspace around DIA. It looks like a big funnel that airplanes come into to land and out of to take off. So, and these are other less busy types of airports here. But this is what it looks like from the air. The yellow is populated areas that pilots need to be aware of when they're over them. And you see other airports. You see a bunch of stuff on this, including some terrain, which is also important. But what they're most concerned about at the FAA are the critical phases of flight. The takeoff and the climb out of an aircraft is at maximum power, slow speed, and a maximum rate of climb. So as the aircraft is leaving the airport, this is the condition that it's in. If it's upset during this period of time, it can be catastrophic in terms of a problem. The other critical phase of flight is the approach and landing. You're at minimum power, slow speed, and a high rate of descent. This is the area that unmanned aircraft operate in, these two critical phases of flight. Most airplanes aren't flying around at 500 feet above the ground. Pilots don't like to be that low in case something happens and they need to deal with it. But you have no choice of being that low when you're taking off or landing. There's been a number of UAS incidents over the last 3 years already, and this is without even any authorized UAS activity from the FAA. There's been about 36 crashes in the last couple of years. So who can currently operate an unmanned aircraft system? A public entity through obtaining a certificate of authorization known as a COA. A private company, such as a land surveying firm, civil engineering company, forensic engineering company, something like that, through a Section 333 exemption, and then manufacturers such as Leica Geosystems through a special airworthiness certificate, or an SAC. So if you are a public entity, you can apply for a COA, and there's some information about what a COA entails. It's aircraft specific, airspace specific, and pilot specific, and it's subject to a comprehensive operational and technical review by the FAA. If you're a private company or a commercial operation like an engineering firm or a photography company or a real estate firm or something like that, then you have to get a Section 333 exemption, and that's what all of the hoopla has been over the last couple of months, because the FAA has finally started issuing these exemptions. It's a complicated, fairly complicated, time-consuming process to petition for one of these exemptions, but whether you're applying for a COA or applying for a Section 333 exemption, we're here to help you with that. We have all of the documentation that you need to submit with your petition to help get authorization to operate. And so I'm going to jump to the place where you need to start, and that is the FAA website, which is faa.gov/UAS. And then it talks about the very thing that I was just talking about. So civil UAS, if you're a private company; public UAS, if you're a law enforcement agency; and model aircraft is completely different. So this is where you need to start, applying for a COA, applying for a Section 333, so on and so forth. In a very brief nutshell, that is the regulatory status. The FAA has issued 333 exemptions. It's generally not very difficult to get a COA, but you're going to possibly have to live with some limitations of your COA until such time that you prove you are a safe operator, you have a safe aircraft, and you have a good training and safety record from the operation that you've already been granted. So in the case of the COAs that have been issued, the FAA has limited them to less populated areas for certain types of operations, and you can petition for an extension of that or an amendment to it to operate over a bigger area, and then the FAA is going to want to see what your track record is as far as safety before they allow you to fly in close proximity to airports or over highly populated areas. The COA process takes roughly about 90 days for the FAA to approve one. The Section 333 has been taking in the 4 to 6 month range. So I'll go back to this. So that's the website. And again, you want assistance with documentation for a 333 or a COA, contact me and I can help you out with that. As far as the future for UAS, increasing the productivity, more data, evidence in less time, having eyes in the sky can be amazingly beneficial for intelligence purposes. Visualization, as you saw from Tony, more deliverables, evidence, court graphics, those sorts of things. You know, the old adage is that a picture is worth 1,000 words, so a video can be worth even more. And it can also be very, very cost effective, because I've seen cases, and Tony probably knows better, where jurors have been taken out to sites to be given field trips. Well, we can do it virtually now and save the time and costs associated with that. Multiple sensors, video, still, thermal, motion, sound can be hoisted into the air with our aircraft. Again, safety, staying out of harm's way, or not having to shut down traffic, or any one of a number of safety concerns can be addressed with the UAS. Of course, you introduce some potential safety concerns by having something in the air, but we want to mitigate that. And then we want to pick the correct platform for the application, whether it's a fixed-wing aircraft or a rotor-wing aircraft. The aircraft, you may have at some point a fleet of unmanned aircraft. You may have a rotor wing. You may have a fixed wing. You may have several rotor wings of different sizes carrying different sensors. So the future is looking like public safety people will have a variety of unmanned aircraft. That concludes my portion of the presentation. We have time for a couple of questions. I'll toss it back to Tony, and we can start going through some of these questions for the next couple of minutes. And the ones that we don't get to, we will try to address in an email specifically to you, because we know who's asking them.
Thank you, Brian. I've been tracking a few questions here. I would just encourage everybody to go ahead and jot down this website address down at the bottom of the slide here. Somebody just asked a question about, is there another source for videos and presentations? There's a lot more information at this particular website. Here's a question for you, Brian. Do you need a pilot's license for the COA?
The answer to that question is, for a COA, no. You do not have to have a pilot's license. The FAA likes it if you have a pilot's license, but it's not required. But you do have to complete satisfactorily a manufacturer training program, which we offer, and then you have to demonstrate your proficiency. For a Section 333 exemption, all of those have been issued requiring pilot's license. So, and there's a couple of reasons for that that's too long to go into in this webinar, but if you are a private company, an engineering firm, forensic mapping, that sort of thing, and you are applying for a Section 333, you can expect that a private pilot license or better will be required, because they've required that on every one, and until they come out with a UAS-specific pilot's license, which they intend to do, that will be the minimum standard.
Brian, I'm getting a number of questions regarding training, and a general one that came in earlier. You know, there's our customers have a lot of different options in the marketplace for sourcing their UAS solution. What is it about Leica that makes it sort of differentiates us and sets us apart, would you say?
On the training standpoint?
On everything, holistically.
Well, first off, we're mapping experts. So we know we don't just leave you with a CD card full of pictures. You know, we actually train you on the entire process to generate the deliverables, not just how to fly the aircraft. That's first and foremost. And the other part of it is that our training is done by pilots. So we are familiar with the regulations and the considerations regarding our national airspace. You don't find that in many other training programs. There are people who have, you know, learned how to fly one in their backyard or something like that, and because the FAA does not yet have specific requirements above being a private pilot for Section 333, it's important that you understand some of the other issues if you are not a pilot in a public safety group, and so that's another distinct advantage. And then finally, I guess, getting back to the mapping experts, Tony showed you that how we integrated terrestrial data with airborne data, and that's something that hardly anybody else can do. They do not have the technology to do that, nor the expertise to do that.
Another question that came up, what happens if one of those 6 motors fails?
You will get a motor failure indicator on the control. It's an audible tone or an audible response. The controller speaks to you and tells you that you have a motor failure, and then the gyro starts compensating for that motor failure. So you do not have to do anything other than the fact that upon getting that warning, you should bring the aircraft back and land it immediately. But the aircraft will basically stabilize itself if a motor goes out. Again, something that a quadcopter can't do.
A question has been submitted about grants. Are there any specific grants for obtaining UAS? I've got to believe that UASI grants or Urban Area Security Initiative grants are probably compatible with acquiring the technology. We are aware of some resources that our police customers can take advantage of to get assistance with regard to those, and I would encourage you to contact me. My email is listed right there. One of the final questions, because we're starting to run a little bit long. One person noticed that the camera is a Nikon. Is the camera interchangeable, is the question.
Yes, we're compatible with about 15 to 20 different cameras. And the camera isn't integrated into the system. It is for some mapping applications. But if there's a particular video camera that you want to use, point of use, first-person viewer system, or a particular still image camera that you can set up to automatically expose and take images every second or 2 seconds or something like that, and it's less than 4 pounds, we can carry it. Doesn't matter whose camera it is.
And then the final question we're going to take, is there an FAA restriction you're aware of yet to hover over a live roadway for accident reconstruction photographs?
The FAA has not granted anyone permission to operate over a live roadway at this time that I'm aware of. There are people that have done that without that legal authority to do so, but you're dealing with a very, very large risk associated with that. And I can see in the future where they would, depending on the aircraft and the pilot's capabilities, but right now I'm not aware of anyone that's been given specific authorization to operate in that environment.
Okay, everybody, that is all the time that we have for today. I want to thank Rick Wyatt and Brian for their presentations today. For more information on the solutions we've discussed today, please visit us at the website shown below, and you're welcome to drop an email to any one of the 3 of us. We're in the process of lining up other webinars for this year, so please make sure to check the schedule at www.leica-geosystems.us/webinars. And I also wanted to let everyone know that early registration is open for our International Technology Conference, HXGN Live, in 2015. It's held in June at the MGM Grand in Las Vegas, and there's an early bird discount for registration. It's an amazing collection of technology and presentations from all of the Hexagon companies, not just Leica Geosystems. As you exit our webinar, you're going to notice that there's a brief survey that we would ask you to take a couple of moments to complete. I want to thank everybody for their time. I know we ran a little bit long. We hope you appreciated the content and the format, and we look forward to speaking with you down the road. Thanks, everyone, and goodbye.